In this video we're going to look at how to deal with improper integrals. Now an improper integral is one which has an upper limit of infinity, or indeed a lower limit of minus infinity, and possibly even both, and or involves integrating a function which is infinite at one or both of the limits, or indeed it takes an infinite value at some value between the limits. So, which of the following integrals are improper integrals? And why are they improper integrals? So reading across the first row, 10 over x to the 0.8 certainly doesn't take an infinite value between 2 or 5. So that's, and we haven't got a limit of infinity or minus infinity. So that's a perfectly good integral. The second one certainly is an improper integral because the upper limit is infinity. The third one is an improper integral because 10 divided by x to the 0.8 takes an infinite value if we try and put x equals 0. Similarly, 10 over x to the 1.8 will be infinite when x equals 0. The integral between 2 and infinity of 10 over x to the 1.8 again is certainly an improper integral because we've got infinity as the upper limit. The integral between 0 and 1 of 1 over the root of 4 minus x squared. Well, between 0 and 1, 4 minus x squared lies between 4 and 3. So it doesn't ever become 0, so 1 over the root of 4 minus x squared is perfectly well behaved between 0 and 1, so that is a proper integral. 1 over the root of 4 minus x squared is going to be infinite when x equals 2, so that is an improper integral. 1 over 4 minus x squared is going to be infinite when x equals 2, so that is an improper integral. 1 over 4 minus x squared between 0 and 1, well, 4 minus x squared simply varies between 4 and 3 between 0 and 1, so there's no problem there at all. That's a perfectly proper integral. The integral between 0 and 4 of 1 over the root of 1 over the modulus of 2 minus x is improper because when x equals 2, the modulus of 2 minus x is 0, so the function we've got, f of 2 if you like, is 1 over 0, which is infinite. So this integral is improper. 1 over the modulus of 2 minus x between 0 and 1 is fine because 2 minus x doesn't take a 0 value between 0 and 1. 1 over the square root of 2 minus x between 0 and 4 again is improper because when x is 2 we're going to have 1 over the square root of nothing, which is infinite. We should be able to evaluate the proper integrals using standard integration techniques. But in this video, what we want to have a look at is how we can deal with and investigate improper integrals. So how do we decide whether an improper integral has a meaningful answer or not? Well, let's start off by considering the integral between 2 and infinity of 10 over x to the 0.8. Now this is an improper integral because the upper limit is infinite. What we're going to do is we're going to consider the integral between 2 and n of 10 over x to the 0.8. So we're integrating 10 x to the minus 0.8. Now the integral of 10 x to the minus 0.8 is 10 times by x to the 0.2 divided by 0.2. And I need the value of that at n, take away the value of that when x equals 2. Now 10x to the 0.2 divided by 0.2 is the same thing as 50x to the 0.2. We need the value of that when x equals n, take away the value of that when x equals 2. So I've got 50n to the 0.2, take away 50 times by 2 to the 0.2. Now, as n tends to infinity, we can see that the value of the integral between 2 and n of 10 over x to the 0.8 tends to infinity. So we say that the improper integral 2 to infinity of 10 over x to the 0.8 does not have a finite value. Now let's have a look at another example. Suppose then we've got the integral between 4 and infinity of 10 divided by x to the 1.5. Now again, this is an improper integral because the upper limit is infinite. And what we're going to do is we're going to consider the integral between 4 and n of 10 divided by x to the 1.5. Doing the integration, 10 over x to the 1.5 is going to integrate to 10 times by x to the minus 0.5 divided by minus 0.5, which is the same thing as minus 20 x to the minus 0.5, or minus 20 divided by root x. So putting the limits in, I'm getting the value of this integral is minus 20 over root n. Take away minus 20 divided by root 4, which is the same thing as 10 take away 20 over root n. Now in this case, if I allow n to tend to infinity, then we can see that the value of the integral between 4 and n of 10 over x to the 1.5, which we know is 10 minus 20 over root n, but as n tends to infinity, this value is going to tend towards 10. So in this case, we can say that the improper integral of 10 over x to the 1.5 between 4 and infinity takes the value 10, and indeed we can write the integral between 4 and infinity of 10 over x to the 1.5 is equal to 10. Now the process that we've used in these last two examples can be used to formalize to a general process that we can use when we have got the upper limit being infinite. So if we want to investigate the improper integral between a and infinity of f of x, then the process we're going to do is we're going to evaluate the integral between a and n of f of x, and then consider whether the limit as n tends to infinity of the integral between a and n of f of x exists or not. If the limit is finite, then this finite value, this limiting value, is the value of the improper integral. If, on the other hand, the limit is infinite, or indeed if there is no clear limit, then no sensible value can be given to the improper integral. If we have to investigate the improper integral between minus infinity and b of f of x dx, then we do a similar sort of thing. We first of all evaluate the proper integral between minus n and b of f of x, and then we consider what happens if we let n tend to infinity in that integral. If the limit is finite, then this limiting value is the value of the improper integral that we're considering. If the limit is infinite, or there is no clear limit, then no sensible value can be given to the improper integral. If we want to investigate the improper integral between minus infinity and infinity of f of x, then we first of all evaluate the proper integral between minus n and n of f of x, and then consider what happens as n tends to infinity. If the limit is finite, then this limiting value is the value of the improper integral. If the limit is infinite, or there is no clear limit, then no sensible value can be given to the improper integral. But there are other types of integrals, improper integrals as well. So what about the integral between 0 and 32 of 10 divided by x to the 0.8? Well, why is this an improper integral? It's improper because 10 over x to the 0.8 is going to give us an infinite value when x equals 0. So the problem is the lower limit at this stage. So what we're going to do to get around this is we're going to consider the integral between delta and 32 of 10 over x to the 0.8, where delta is a small positive number. Now that is certainly a proper integral, and we can evaluate that integral fairly easily. So the integral between delta and 32 of 10 over x to the 0.8 is the integral between delta and 32 of 10x to the minus 0.8. Integrating 10x to the minus 0.8 gives me 10x to the 0.2 divided by 0.2, which simplifies to 50x to the 0.2. I've got limits 32 and delta. So that gives me 50 times 2, because 32 to the 0.2 is 2. Take away 50 times by delta to the 0.2. In other words, I've got 100 minus 50 delta to the 0.2. Now, what I really want to do is I want to push delta towards 0. If I let delta tend down to 0, then the value of the integral that we've got was 100 minus 50 delta to the 0.2, but as delta tends to 0, that's going to just tend to 100. So we can now say that the improper integral between 0 and 32 of 10 over x to the 0.8 takes the value 100, and we write it as the integral between 0 and 32 of 10 over x to the 0.8 equals 100. Now again, we can use this example to formalize the process for improper integrals, where the integral is improper because the function is not defined at one of the endpoints of the domain of integration. So if we want to consider the improper integral between a and b of f of x, where the integral is improper because f of a is undefined, then we start off by evaluating the proper integral between a plus delta and b of f of x, where delta is a small positive number. We then consider what happens as delta tends to 0 to the value of that integral. If the limit is finite, then this limiting value is going to be the value of our improper integral. If the limit is infinite, or there is no clear limit, then no sensible value can be given to the improper integral. And we do a very similar thing if the problem is that f of b is undefined. We start off by evaluating the integral between a and b minus delta of f of x, where delta is again a small positive number. And we then consider what happens to that integral as delta tends to 0. If the limit is finite, then this limiting value is the value of the improper integral. If the limit is infinite or there is no clear limit, then no sensible value can be given to the improper integral. Finally, we need to consider how to decide whether an improper integral has a value or not when the thing that's causing the integral to be improper is the fact that there is a point within the interior of the domain for which the function is not properly defined. So let's consider, for instance, the function g here, where we've got g of x is defined to be x plus 1 if x is less than 2, and g of x is 1 over the root of x minus 2 if x is greater than 2. Now let's suppose then that we want to evaluate the integral between 0 and 6 of g of x. Well, this is an improper integral because g of 2 is not defined. So we need to think of some way of getting around that. And what we certainly can do happily is split the integral into 2 bits. Think about what's happening between 0 and 2 minus delta, so a little bit before x equals 2, and then from 2 plus delta up to 6. So we split the integral into 2 integrals, each of which are proper integrals that we can evaluate. So the expression we're going to consider is the integral between 0 and 2 minus delta of g of x, and then later we're going to have to consider the integral between 2 plus delta and 6 of g of x. For the integral between 0 and 2 minus delta of g of x, that's the same thing as the integral between 0 and 2 minus delta of x plus 1. So that gives me, when I integrate x plus 1, a half x squared plus x. So putting the limits in, I've got a half of 2 minus delta squared plus 2 minus delta. Take away 0 plus 0, which simplifies down to 4 minus 3 delta plus a half delta squared, between 2 plus delta and 6 of g of x, which gives me the integral between 2 plus delta and x of x minus 2 to the minus 0.5. Integrating x minus 2 to the minus 0.5 gives me x minus 2 to the 0.5 divided by 0.5 with limits of 6 and 2 plus delta. If I put 6 in, I'm going to get 2 times the square root of 4. And if I put 2 plus delta in, I'm going to get 2 times the square root of delta. So in other words, the integral here that I've got for the integral between 2 plus delta and 6 of g of x dx gives the final answer of 4 minus 2 root delta. So I now need to combine my two answers. So if delta is a small positive number, then we know that the integral between 0 and 2 minus delta of g of x plus the integral between 2 plus delta and 6 of g of x gives me 4 minus 3 delta plus a half delta squared plus 4 minus 2 root delta. Now what we're really interested in is what happens as delta tends to 0. And as delta tends to 0, this value just gets closer and closer to 8. So we are now going in a position where we can say that the improper integral between 0 and 6 of g of x takes the value 8, and we can write the integral between 0 and 6 of g of x to be equal to 8. And this now suggests to us what to do if we have an integral of g of x between x equals a and x equals b, where there is a value c in between a and b for which g of c is undefined. And the process is to first of all work out the integral between a and c minus d of g added to the integral between c plus d and b of g, where delta is a small positive number. We then consider what happens to the limit as delta tends to 0 of the sum of these two integrals that we've just worked out. If the limit is finite, then this limiting value is the value of the improper integral between a and b of f of x dx. On the other hand, if the limit is infinite or there is no clear limit, then no sensible value can be given to the improper integral. So during the course of this video, we've looked at what constitutes an improper integral and the processes that we need to take into account if we want to see whether an improper integral has a finite value or not.